Hey folks, JListExec here. Before we get into probability, I want to take a moment to just talk about this this macro phase here. I had some questions related to this about how I went about deriving this macro phase. So I'd like to show you how I went about that. There's going to be a couple of things in here that'll be useful for you for other things as well. So just as a little bit of a reminder, in polymetric mode, if you remember, when we change the phase relationship of our two sequences, say if I make it 5/4, the amount of times it's going to take for our bar to cycle is going to change depending on a certain calculation that's done on these two sequences to figure out when they link up again. So we'll just watch this happen here. So 5/4, we've got 1 bar, 2 bars, 3 bars, and then on the 4th bar, it cycles again. So a 5/4 polymetric sequence might be really useful if you want something to kind of evolve over the course of 4 bars. So how do we figure out how many bars it's going to take, or how many cycles of these two sequences is it going to take before this links up again? So if we have a look inside our patcher, and we remember from last week, I just copied these sub-patches into the patch and didn't really give you a lot of explanation about what was happening there. I actually cut that from the video to keep it to around 20 minutes. So instead of opening these up, what I'm going to do is delete them, and we'll do this from scratch. So the way that you might approach this is you could just use the rate operator, and you could use lock or cycle mode for your sync, and you could just pass in the master phaser and then multiply that by a certain number. And that's initially the way that I approached it. Now, what can happen here is that you can make the change during the wrong bar, and so you'll have problems aligning the phase of your main phaser back with your macro phaser. So let me do a quick demonstration of what that looks like. So give you a demonstration of the problem, and then I'll show you the solution. All right, so in order to figure out what the correct rate that you would need to apply to your rate operator, if you're going to approach it this way, is that you need to be able to use these numbers in order to derive how many cycles it's going to take. And the way that you derive that is a really simple operation, something you probably learned about in elementary school. And that is something called the lowest common multiple, or least common multiple. And the way that you derive the lowest common multiple is that you can derive it. You can see here, if you just Google LCM, you'll see the formula comes up. And so you can use this other calculation, which is the greatest common denominator, as part of deriving this. And that's exactly what's going on in this subpatcher here, which Fabio rightly pointed out wasn't supplied with the previous example patch. So I'll fix that for the previous upload. But I want to show you why we're selecting this using CodeBox in Gen. And CodeBox is something that where I'm really keen to get this series up to, because often when I use Gen, I basically almost only ever use CodeBox. So I'm really keen to get you folks to using CodeBox. I know there's a few people out there that kind of look at this stuff and don't know what to do with it and throw it away. And that's okay. In this instance, I actually was trying to come up with my own method for deriving the lowest common multiple, just using objects. And in many cases, this is a perfect example where it's way simpler to do it with CodeBox. Now, there's a part of this that I also want to highlight here, and that is that this is an example that is included with your MaxMSP install. If you go up here to your menu bar and you click on examples, that's off the help item in your menu bar, and go to Gen, you'll see a whole world of Gen examples here. And if you haven't already come across these, this is an excellent way to get to explore Gen. There's a whole bunch of different examples here that are awesome. So I'd encourage you to look around there. Lots of stuff you can have fun with. One of these is GCD and LCM, and this is an example, I believe, by Graham Wakefield. And this is exactly what I'm using in the patch, because it's a very neat and clean way to derive this. So this is a perfect use case for, you might see this in the examples and go, why the heck would I ever use this? And to figure out phase relationships and stuff, these simple calculations are going to be really useful. So if I do 5 over 4, you see the greatest common denominator is 1 and the least common multiple is 20. So how do those numbers, how are they useful in our patch? I've just got the same code box patch coming out here into my 7th outlet. So if I just duplicate this number tilde box and connect it up, you'll see that we've got this number 20 here. So if I change these numbers, if I make this, 6 over 4, we get 12. Or 6 over 5, we get 30. Or something simple, we make 4 over 4, and we get 4. So how do we turn this into the amount of bars? All we need to do is divide this by the amount of steps in our first sequence, or divide it by the amount of steps in our second sequence, and you'll get how many times this sequence needs to repeat before we get back to phase lock. So knowing that, I've just used this expa expression operator here as a means to grab my param. It's just kind of like a bit of a hacky workaround to get this number rather than use a patch cable or a send and receive pair. And so I'm pumping in the amount of steps for each into our GCD LCM. And then if you just want to have a look, what's coming out is the lowest common multiple. And so that's calling this function here. And then this function is actually calling this one up here. At a later date, we'll get into the nitty-gritty of that, but at the moment, you can kind of trust that it's giving us the right number out. Out of here, we're getting the number 4 for a 4 over 4. And then if we divide that by the number of steps in the first sequence, that's how many steps it's going to take before we get back to phase lock. So you would think that perhaps that is finished, right? Like if we make this something that isn't going to be 1 bar, like 4 over 4, if we change this to back to our 5 over 4, where it takes 20 steps to repeat, is that we are using this number, comes out into here, and it's multiplying our main phaser by this amount. So if I change this outlet here, so we're multiplying our main phaser by 4, so we want this to repeat 4 times, right? And then this should link up. So you would think that if we just put that into our rate operator and multiplied our main phaser by 4, that would be all we need to do. But what you'll notice here is, you'll see that this macro phaser, the phase isn't lining up with the actual one of these two things. It's lining up with the bar. It's doing its job in this phase being 4 times as long, 4 bars long. But getting it to start in the correct place, like having its actual phase be correct, is a problem that we can't solve with the ordinary rate operator. And so that's why if you have a look at the subpatcher from the previous example, you'll see a different version of the rate operator that I had to kind of make myself. Now there's probably a better way to do this, but I found that this is the best way for me to do it. So let's go ahead and make that. So what we'd like to do is we'd like to be able to reset this rate operator. And that's what we're doing in this GED subpatcher. To give you a bit of context, if you do this in MSP with the rate tilde object, if we go to the help patcher, you can send in a symbol here. You can send in the word reset, and it will lock the output to the next phase that resets. And that's what we'd like to do. We'd like to be able to control, like if this macro phase is one bar off, it's like 1 bar out of phase or 2 bars out of phase, we'd like to be able to automatically hit a button and lock it back to that first bar. And you can do that with the rate tilde object in MSP, but because in Gen we can't work with symbols, we can't work with words or strings, we need to come up with our own method to do it, because there's no, to my knowledge, there's no way to do this at all with the rate operator. So necessitates making our own. It's a good opportunity to show you how you might, if an operator is not doing the thing that you want it to do, you can kind of just make your own version of it and save it as an abstraction. That's exactly what we're doing here. So we've got our brand new reset rate subpatcher, and the basic method that we're going to use to recreate the rate operator is that we'd like to have it function pretty much the same way, but we'd like to be able to add this reset ability. And that is all based on the fact that you can reset the phase if you use the phaser operator in Gen. If you hover over the right-hand inlet, you'll see that a non-zero value will reset the phase. So we're going to use phaser as the main weapon for recreating the rate operator. So in order to replicate that functionality, we need to know what the input phaser that we're going to use is, and in our case, it is this main phaser. We want to use this number that we've derived previously using the lowest common multiple. We want to basically make this take 4 times as long. So we need to know firstly what this frequency is that's driving this main phaser. And if we look out here in the parent patcher, you can see that translate is helping us figure that out. The frequency of 1 bar is 0.666 hertz repeating. And so translate is helping us out here in the parent patcher. And you might be tempted to look for something like translate in Gen, and you won't find translate. And so another alternative approach that you could take is that you could use translate out here in the parent. You can make a new inlet and you can pump that number in. But what I want to show you here is to try to get in the habit of using processing in your Gen patcher. Try to think about things contained within Gen, because there's a really simple calculation that you can do to derive the frequency from an input phaser that's coming in. And you can derive not only the frequency, but you can also get the period. So I'll quickly show you how to do that. So if we perform a delta calculation on the incoming phaser, so if we the difference between the current sample and the previous sample, and then we multiply that by the sample rate, and then if we just change this outlet here, you can see that the phaser, the hertz that we're using to clock this phaser, you can see we're extracting that on the other end. And so if we decided to change this to 2 bars, you can see that this is reflected in this method to extract it. And so this is one way, just using the delta calculation and multiplying that by the sample rate, you can get the frequency. But we can also get the period of one oscillation in milliseconds. So in order to derive the period of one oscillation, we can use the reciprocal and then multiply that by 1000. And so now we see that for 2 bars, it will take 3 seconds. So putting this back to 1 bar like we had previously and removing the period derivation, because we're not going to be using that in this case. So we're going to go back to using this frequency that we've derived from our input phaser, and we're going to use that to drive our phaser for rate. So in order to get our phaser to work like rate, we'll need to multiply this number that we've derived here, which is the speed in hertz, the frequency. And then like we would use rate, we would just be able to multiply or divide that by a number and then use this inlet here to reset it. Before we do that, there's actually a problem with this method that we need to fix, and I'll show you what that is. If we connect up this outlet, this is coming out our 7th outlet. So if I connect this up to our macro phase here, like this, you'll see that there's actually a change here. This number that we're seeing in the live.scope is this 0.666 repeating. But you'll see that when the phase from the incoming phaser gets to the end of its cycle, we drop down to this negative number. And that's because the current sample is 0 and the previous sample is 1. It's the apex of this phase. And so we want a continuous number. We want to filter out this drop at the end of the main phaser. We want to get rid of that because our phaser inside here This phaser, if we plug that in there, at the end of the cycle, it's going to jump down to a negative number. We need to iron that out. So we can use a less than 0 for our condition that we applying to our ternary. And so if this condition is true, if it's less than 0, we actually want to use the previous sample. We don't want the current sample. We don't want this sample that's underneath this value that we really do want. So we can use the history operator. That's really useful for this purpose. And then if the condition is false, as in it's not a number that's under 0, we can just pass in the number that we've got, as in the current sample. So now if I connect this up, we should have no discontinuity at the end of our phase, and that's exactly what we're getting. So this is basically our finished replica of rate, but now we've got the ability to reset this phase. So if we sort of chunk these two things together, this is basically our rate operator, and this is just the part that's driving it. So our second inlet, let's make this the inlet for our rate multiplier. So I've made two new inlets here. One is for the rate, the multiplication or division, just the same way that we'd use rate. We should be able to put in a 4 through here and get what we want. And then the other is this non-zero reset. So just by adding the exclamation mark to the front of it, we can reverse this operation. So we're actually dividing the amount of steps by the lowest common multiple. So now we just need to figure out the correct time to reset our phase so it locks in. You can see that we're not aligned here. And the simple way that we can do this is that we can use the phase location of these two rate operators. So we'll bring them over here. So what we need to do is supply the rate coming out from our first sequence into our first inlet, and the second rate into our second inlet. So to make this really simple, we'll just multiply these numbers by each other. And that's just an easy way to combine these two numbers together. And then we can use another delta operation on these. We'll use this to reset the phase. And so that you can see that we're now aligned back with our correctly. All three phases are lining up together. So the other thing that I did in my reset rate subpatcher is that I wanted to emulate the cycle attribute of sync, the sync mode cycle. And so I'll quickly show you that too, because I think that might be interesting for at least for some of you. All right, so in order to make our emulation of the cycle mode for sync, for rate, what we're going to want to do is we're going to want to, whenever we make a change to our rate multiplication that's based on the calculation that we're doing to our sequence lengths, we want to kind of hold off this change to the multiplication and the phase. We want to hold that off until the next phase cycle that's coming in from here. So we already have a method to detect the phase cycle of this input phaser, and that's what we're doing here with this less than 0. So we can pass that into our second inlet, and then we can pass in the actual number into here. So this is kind of acting as a little bit of a buffer. And then we're going to pass out this number. We're going to pass it out here, and then we're going to reset the phase here. So you'll need an inlet, you'll need 2 inlets and 2 outlets. And one object that's going to be really useful to do this with is the sample and hold operator. And this functions in the way that you would assume if you've ever used a sample and hold operator in Modular or even in Max. And one thing I like to do is, just for good luck, is set a constant here for the threshold. So whenever it's above 0.5, it'll pass through. We're only going to deal with zeros and ones here, but it's good to just set that threshold, I find. So this second inlet is the control signal. So when the number is above this threshold, it will hold a new number. It will sample it, and then it'll hold it. So the number that we want to sample is this inlet here, coming in from our rate value. And we want to use this second inlet here. So I might push these up against each other. And we just want to pass that through. So when it's the start of the bar, we'll push that through. And that's going to do the first part of our cycle emulation. The next part that we want to do is we kind of want to make sure that the phase is resetting at the same time. So what's going to be useful here is we're going to need an operator, the AND operator. And this is a conditional operation that means that both input values need to be true to pass through a 1. And if you remember here on our phaser, a non-zero value will reset the phase. So anything that's not a 0 will reset it. So we're going to have two conditions here that need to be met for the phase to be reset. We want to be able to determine whether we've changed this, if we've made a change to our incoming rate since the last time we changed it. So an easy way to do that is we can use an equals operator, or we might invert that. We might use a not equals operator like this. And so this will form the basis of one of these conditions here. The other condition is going to be whether it's time for the next phase cycle. So if it is time if it's the beginning of the next phase cycle, this is one condition, and the other condition is, have we changed this rate multiplier since then? So we use a history operator to view the last value that's come through here, because what's actually going to happen is at the beginning of the next phase cycle, this is going to change. So we actually need the previous sample. So the history is going to form the this part of it, and then the other part is this. So this is one way that you could approach creating a cycle emulation. You can see that the number for multiplying our rate, we're holding that off until the next phase cycle. And then we're also making sure that we reset the phase at the correct time, and that we only do it once. So that's what all this logic is here for. Cool. So for those of you who are wondering how I calculated that, that's the method that I used. Encourage you to develop your own methods for doing stuff like this, and I'm sure there's probably a more efficient way of doing this as well. So that's a bit of a tangent. Next week we're going to jump back into probability, and going forward we'll get CodeBox, and we'll do some cool stuff with with Euclidean sequences and stuff like that, ratcheting stuff. So we're getting closer to doing the fun stuff. Cool. Hope you got something from that. I look forward to seeing you next week. See ya.